Einstein would be thrilled to have the opportunity we have today. On August 12th of this year, a total solar eclipse will take place. It is the same kind of eclipse Einstein needed more than a century ago. An eclipse that would help put one of the most important predictions of his general theory of relativity to the test. Just like more than a century ago, today's circumstances will allow the eclipse to be seen in totality only from certain parts of the planet. And you might be wondering, why was it necessary to observe a total eclipse? Why wouldn't a partial eclipse be enough? The answer lies precisely in what Einstein wanted to demonstrate, that the enormous gravity produced by an object as massive as the sun could curve the space around it, and as a consequence, change the path of light passing nearby. To understand this better, imagine space as an enormous surface. When we place something as massive as the sun on that surface, the space around it becomes distorted. Now imagine a beam of light coming from a very distant star and passing through that region. As the light travels through the space distorted by the enormous mass of the sun, it follows that curvature, slightly changing its path. Of course, space is not literally a fabric that bends or sinks. This is simply a way of visualizing something far more complex, the curvature of space-time. But Einstein had a problem. How could something like this actually be tested? The sun had the enormous mass needed for the experiment, but its own brightness made it impossible to observe the light from stars appearing very close to it in the sky. And this is precisely where a total solar eclipse comes into the story. For a few extraordinary minutes, the moon completely covers the bright disk of the sun, blocking most of its intense light. And then, something remarkable happens. Stars that would normally remain hidden by the sun's glare can become visible around it. And if Einstein's theory was correct, the light coming from those stars would have traveled through the space-time curved by the enormous mass of the sun before finally reaching us. The effect would be incredibly small. But it could be measured. From Earth, those stars would appear to be in a slightly different position from where they should actually be. And that tiny difference could become evidence of something extraordinary. That gravity could change the path of light. But getting there was not going to be easy. Several attempts and expeditions were needed. Some failed. Others were interrupted by circumstances that had absolutely nothing to do with science. There were arrests, confiscated telescopes, suspicions between nations, war, bad weather, and failed observations. At one point, scientists were preparing to look toward the sky and test an idea that could completely change our understanding of the universe. While here on Earth, countries were preparing to fight each other. In 1914, German astronomer Erwin Freundlich traveled to Crimea with an expedition hoping to observe a total solar eclipse and test Einstein's prediction. But just as they were preparing for the eclipse, the First World War began. Freundlich and members of the expedition were arrested in Russian territory, and their astronomical equipment was confiscated. The eclipse came, but Einstein's prediction could not be tested. And strangely enough, that failure may have been fortunate for Einstein, because in 1914, his theory was not yet complete. At that time, Einstein's calculation for the bending of light was only about half of the value he would later predict. Einstein was still working, still correcting his equations, still trying to understand exactly how gravity, space, time, and light were connected. Then, in 1915, everything changed. Einstein completed his general theory of relativity. And with the completed theory came a new prediction. Light passing close to the edge of the sun should be deflected by approximately 1.75 arcseconds, almost twice the value Einstein had calculated before. So the failure of the 1914 expedition suddenly takes on a very different meaning. Einstein had lost an opportunity to test his prediction. But perhaps, he had also gained the time he needed to get it right. It is almost ironic. Humanity was getting remarkably close to understanding something as profound as the curvature of space-time, while at the same time, here on Earth, we were entering one of the most devastating conflicts in our history. And Einstein would have to wait. He needed another total solar eclipse. The opportunity would finally come 5 years later. It was in 1919 when Arthur Eddington became one of the central figures in the story that would eventually turn Albert Einstein into the most famous scientist of his time. On May 29th of that year, 2 expeditions traveled to very different parts of the world. One of them, with Eddington, went to the island of Principe, off the western coast of Africa, while another group traveled to Sobral, in Brazil. It was an extraordinary scientific effort, especially considering what the world had just been through. Scientists from countries that had recently been on opposing sides of a devastating war were now working toward the same goal, putting political divisions aside and looking together toward the sky, in an attempt to push humanity toward new scientific horizons. And accomplishing this in 1919 was anything but simple. Delicate telescopes and photographic equipment had to be transported across enormous distances, installed and calibrated in remote locations, while the scientists also had to deal with unpredictable weather and the simple fact that nature would give them only a few minutes to obtain the observations they had been waiting years to make. In Principe, the situation became particularly difficult because clouds threatened to ruin the observation. After all the calculations, the previous failed attempts, the war, the arrests, and the confiscated equipment, years of effort could once again be lost simply because the sky refused to cooperate. But on the 29th of May 1919, the moon finally moved completely in front of the Sunday. During those precious minutes of totality, photographs of the stars surrounding the darkened sun could be taken, and those images could later be compared with observations of the same stars when the sun was no longer in that region of the sky. The measurements were consistent with the remarkable prediction Einstein had made with his general theory of relativity. Light passing close to the sun was being deflected by the curvature of spacetime produced by its enormous mass. What happened that day went far beyond the observation of an eclipse. Humanity had found experimental evidence supporting a radically different way of understanding gravity, space, and time, and from that moment on, our vision of the universe would never be quite the same. More than a century later, on the 12th of August 2026, nature will give us another opportunity to witness a total solar eclipse. Of course, today we no longer need an eclipse to prove Einstein's theory, but when the moon once again covers the sun, we will be witnessing the same extraordinary astronomical phenomenon that once gave scientists the opportunity to put one of the greatest ideas in the history of physics to the test. And here at Cosmos Reframed, this is only the beginning. Very soon, we will show you historical documents of extraordinary value, pieces of history that have survived for more than a century, and that will allow us to explore some of the moments when humanity completely changed its understanding of the universe. So don't forget to follow Cosmos Reframed, and if you have the opportunity to experience this coming eclipse, enjoy it, but also remember what happened when scientists looked toward that same darkness in 1919. Sometimes, we need the sun to disappear for a moment to see the universe more clearly.